Okay, so let us start our 27th lecture on power system operation and control. Here we discussed in the last class about hydrothermal scheduling. We'll see one numerical example and that will give you a quick understanding. Means you have to solve that example. I'll just give you an example. We can also discuss that in the tutorial session, and then we'll end with the hydrothermal scheduling and we'll start unit commitment. So I'll tell you what is the difference and why there's another topic which is unit commitment. What exactly is different, what exactly are differences from the economic dispatch and hydrothermal scheduling or in OPF. What is the difference between everything? That I'll explain you, and before starting the new topic. Okay, so we discussed in the last class about hydrothermal scheduling, and I told you that what exactly is the issue, why we want to separately handle hydro generators. So, can anybody quickly tell me what all are the issues, or just your thoughts? May not be all correct, but yeah, please. Why we want to handle this hydro generators in a separate sense? Anyone?
Sir,
Yes.
due to less ramping capability of thermal generator.
No, but that is the separate thing. That is the operational aspect. Basically, that we are going to discuss in unit commitment. But here we are just talking about why we want the hydro generators, because that ramp up limits and all is basically the operational aspect where it helps in system operation. That we can say for the diesel and gas generators also, right? Because they also provide ramping capabilities. But what is specific for hydro generators? Anyone? Adam, Bahaldeen, Omar, Arun. I don't know who all are here today. Let me just see. Ali, Lukesh, Nivedita, Prasanjit, Adyasha, Pushpendra. Anyone? Or was it not clear in the yesterday's class? Please just make it a random attempt. Don't worry about if you can be wrong. So like one of you said about ramping, it's okay, no problem.
Sir, for the point of the economic view and also the limitation of hydrogeneration. So for that reason, we are going to
So
use
yeah, so what all
artificial
are
scheduling.
the limitations of hydro generator? And if you can answer that, then again you can easily connect why hydro generator has to be treated separately. I agree. Your point is correct that there are some limitations, there are some additional factors which we have to consider. But what all are those factors? Anyone?
So the generation of a hydropower plant depends upon many factors such as the water available and from season to season it also varies. And they are not like all hydropower plants are not same. Like they depend on at what location are they are present and many other factors. And Also, the hydro energy is limited, and so you need to think about their coordination and everything.
Yes, partially, yes, yes, you are correct. So yeah, obviously all the hydro generators are not same or not identical. Every hydro generators are different. Obviously, they depend on the location where it is installed. You can say that two coal-based power plants of having a capacity of 500 megawatt, you can make those two power plants an identical sense. If all the technologies and everything is same, then you can make two identical power plants of coal-based generators. But in hydro, you cannot make two identical power plants because there are multiple factors. One is basically the dam where you are building, and that dam will have all the dams in the world are having different water storage capabilities. Also, obviously, all the dams are built on rivers, and all the rivers have their own seasonal flow and seasonal volume of water changes based on season. So these factors are there. Also, the size of the power plant what you can build is also limited by the size of the dam or size of the water storage capability. Also, it depends on the location because there are some regulatory norms that because obviously in the downstream of the dam there will be cities, there will be agricultural lands which needs water for their day-to-day activity. So due to the government regulations, not only just within a country but within a state also. So in India, if a dam is built in a one state and if a dam is built in another state, both will have different terms and condition which they have to follow to ensure the power of the water supply for the downstream. They cannot block the complete river. So there are various norms because of which they are again limited by how much they can generate and at what rate they can generate. So these factors are there which make the hydro power plants different from the conventional thermal or nuclear or cascaded way. In a they can have a pumped storage features. So if those features are there, then again the operational variations or operational feature of that hydropower plant will be different than the other power plants. That also makes additional difference. So we saw that when a plant is there with a normal upstream storage, basically there is no other thing, water is coming, there is natural storage is there because of which the dam is filling up, and then you discharge the water and you get the power generation. So this is the conventional way. Cascaded hydropower plants are there where you need to ensure this water transport time delay because cascaded means there can be series of dam built on the same river in different locations. So basically what happens is if the dam located in the topmost position, the way that dam releases the water, then only the dam which is located in the downstream can operate based on the operation of the previous dam. So this connection is there, and this connection is taken care by this water transport time delay, because you also need to ensure that if let's say two dams are built on the same river having a distance of 100 kilometers, so you need to ensure that if the dam which is in the upstream, once it discharges the water, the water takes probably some time to reach at the dam located at the downstream of the river. So this time delay you also need to take care when we are talking about cascaded hydropower plants. And lastly, the pumped storage. And here we discussed that if you have, let's say, a storage capability, so what you can do is you can generate when the power prices are very high or the loading conditions are very high, then you can generate from these power plants and again pump back the water which you are discharging when the loads are very low, and when loads are very low then the prices are very low. So you can pump back the water to the storage area, and you can use it whenever the peak periods are there. So these features are there in some of the power plants, pumped storage plants. So these features make the every hydropower plants different from each other, and these features, specifically these features, need to be handled or taken care separately in the optimization model or in the OPF. And we have to add the constraints very carefully in the optimization model. So I hope now it is clear to everyone that why this hydro generators have to be handled separately. Is there any question now? Is there any query now? Because many of you were unable to visualize this. Thanks to Nivedita that she answered that. Any query as of now? I hope now it is clear why hydro power plants are handled separately. So I'm not going into all the things again, because you can easily see the previous lecture. I'll upload the lecture, the previous lecture also by today. I forgot to upload that, so I'll upload it today. Any query? Okay, so now this mathematical model we have seen here. I'm just going to quickly recap this, that we have to ensure a power balance. This power balance is ensured in this equation. Here we are ensuring power balance, and these two are the thermal and hydro generator power limits. Q is the water discharge, what maximum or minimum it can do at a particular time interval, and the total discharge should be equal to Kj. Kj is the total water available with the hydropower plant, which he can use for power generation for a day, because this is, we are calculating for a day, because here we are having a 24-hour model, but because this is a short range problem. So if we are talking about long range will be a yearly model. Short range is generally hourly, a day or a week problem. Right now here there is one equation which is missing here, is that the discharge is actually equal to A plus B pH plus C pH square. So this is the discharge which connects, this equation actually connects these two equations, because obviously discharge can be, because you can see here that power generation by hydropower plants can be any value, it is not connected with discharge. So here this is the equation which is missing here. So if you add this discharge equation, then you can connect the discharge is also limited, or the hydropower generation is also limited by the discharge limits. So this is there, which I have discussed in the next slide, but again just wanted to give you an idea here. So we talked about that there will be we have, for solving this we'll calculate a Lagrange function, and we know that Q is also a function of this pH. So basically you can write it as like this, that QH is a function of pH, right? Or here we are assuming that it's a quadratic function, but it can be any other random function. So that's why if we take the KKT conditions, or if we take the derivatives, you will also take the derivative of Q with respect to pH. So whenever you are taking that, so if let's say I'll show you from this slide, here you can see that we have taken the derivatives in terms of lambda, derivatives in terms of here we have taken lambda, here we have taken gamma, here we have taken PT, which is the thermal power generation, and here we have taken pH, and for taking pH we are taking derivatives of dq by dpH. So that is coming here, because dq by dpH is also a quadratic function, so there will be some derivative for this. And we discussed that this lambda is the price, which is same if you just take the lambda on the left hand side. So lambda will be equal to dft by dpg. Let me just make it. So here if you see that the lambda, if you can take it on the right hand side, then it will be dft by dpt, which is the incremental cost of the thermal power generator. And then in the fourth equation here again, if you take lambda, will be equal to gamma dq by dph, which will again show you that this is the price for the hydro power generations. Now here we also told earlier that this gamma j is nothing but the price corresponding to the this is the price for the volume of the water. So the volume at which the water is being discharged, that rate of discharging the volume has a price of every water. Although we say that the water does not have any price, but you can, from the mathematics, you can easily calculate the price at which the water is being discharged. So there is you can calculate the price of water from here. Right, so this was the recap of the previous lecture. Any query till now from here? Okay, good. If no queries, then we can go ahead and see. We have seen this type of problem. We can easily solve using either lambda iteration method, or you can solve this problem either by Newton's first order method, Newton's second order method, or interior point method, because obviously it's a non-linear one. So you can use any method of your choice to solve this type of a problem. Right, so let me just give a small example for solving this problem using lambda iteration method. That is, basically you can assume gamma j for all the hydro generators, and then once you know the gamma j values, you can easily calculate equations 1, 3 and 4. So 1 was corresponding to the power balance equation. 3 is, so basically only gamma is the unknown compared to economic dispatch, if you see. So if you just know the value of gamma, or if you assume the value of the gamma, then all the problems become similar to the economic dispatch problem. So just assume the value of gamma, any random value, and then you can calculate the economic dispatch type of a problem. And then once you solve that problem, and then at the end you update the gamma as we did in the Newton's first order method. So you keep on updating the gamma, and eventually it will converge, and it will give you a solution at a global or at a local optimal solution. Right, so this is what you can do, and you can get the solution. This is just one suggestion, but you can also solve using Newton's first order, Newton's second order, and interior point method. So you are free to choose those algorithms. Now, obviously, again, as I mentioned here, that there are 2-3 difficulties from the practical point of view. One is basically we are assuming here hydro characteristics as quadratic, basically Q as a function of pH. Here we are assuming this as a quadratic one. So as you obviously, as you have seen earlier, that we cannot treat it as a quadratic. Obviously there are a lot of factors which plays an important role here. So this is not practical, but theoretically, or even in the industry sense or the practical sense, people use some sort of assumption for estimating this characteristics of hydro plants. Also, again, the lambda iteration method, which I told you before, in that the adjustment of gamma is extremely difficult. So it has a very strong interaction between gamma and lambda, and you cannot easily assume gamma and solve this problem. So therefore I recommend everyone to please solve it using the Newton's first order method or Newton's second order method or interior point method. So those methods are much more easy to solve compared to this lambda iteration method. So obviously in lambda iteration you will require more number of iterations to converge to a solution. Also the last, which is very difficult to manage, is basically the head. So you can obviously see that the head is basically the water level at the dam, because whatever is the value of the head, based on that you will have enough potential energy to basically which will be converted into a kinetic energy, and that power flow or the discharge flow of the water will be decided. So the speed of the water will be decided, which will eventually turn the turbine and eventually rotate and generate power. So that head is very difficult to decide or predict. Also, the in case of cascaded plants, this becomes even more difficult, the judgment on the head of the dam. So this is also very difficult. So there are various difficulties in hydropower plants. So therefore we again was studying this hydropower plant separately than the conventional power plants. Now I'll just give you a quick background that how practically system operators runs this hydropower plant. So what they do, that this discharge equations and this q this equation, and then the discharge equation, that is sum of q should be equal to kj. These two equations are not considered by system operator. So practically I'm just giving you an idea what exactly a system operator does. Is basically they treat all the generators, even these hydro generators, thermal generators, diesel generators, gas generators, nuclear generators, every generator as a same generator. They do not differentiate between them. What exactly they do, that they collect the bids similar to what you were seeing in economic dispatch, or in or different generators were giving their bids. So similarly here also they only tell hydro generator that okay, what is the volume, or sorry, what is the quantum. So basically they will say that they will generate between, let's say it's a 100 megawatt power plant, so they can say that they can generate between 0 to 100 megawatt at, let's say, 1 rupees per kilowatt, or if, let's say, if I convert it into megawatt, it will be 1000 rupees. So basically what it happens is these hydro generators, they are also told to give the similar bids, and all the generators are actually in the power system. They request them to submit their similar bids, that what is the range of power they are interested in generating, and at what price they are able to provide that power. So this is decided by individual generators. So what they do here for the hydro generator is basically hydro generators provide these information to the system operator, and these discharge equations and will be taken care by the hydro plants itself. So they will ensure that these constraints are satisfied. So let's say if a system operator tells them to generate 80 megawatt, so these hydro power plants will ensure that their discharge is enough to take care of all these parameters. So basically it is in the different sense. You got the idea, right? So in the economic dispatch they do not include these discharge equations at the system operator level, but those discharge equations are included in the power plant level, and eventually hydropower plant just gives this information that okay, they are interested in selling this much range of power at this price. So this is what they just give to the system operator. So I hope you got the idea or the connection between the practical operational aspect of hydropower plant. So it is much more simpler in practice, but theoretically it is much more difficult. So that's the reason why they have simplified in the practical situation. Any queries as of now?
Sir, can you just repeat that point related to the price and the megawatt?
This quantum one?
Yes, exactly.
Okay, so basically, for whenever a system operator, or let's say in the market, we are going to see that course in detail in the next semester, but for just for your understanding, that there is a system operator. I'm just going to explain it in a much more simpler way. So there is a system operator which actually collects all the bids. So bids here, all the generators, either it is hydro, thermal, nuclear, gas, diesel, all these generators, they gives a bid or submit a bid to the system operator where they say that they will be generating, let's say, 10 megawatt to 50 megawatt. They can give any random value. It is decided by the power plants, and they can say that I'll be generating between 10 to 50 megawatt at, let's say, zero point 0.5 rupees per megawatt, or it will be in kilowatts, but you can convert. Let's make it simpler. I'll convert it and then tell you. So it will be, let's say, 500 rupees per megawatt. So I just multiplied it by 1000, right? So all the generators across the world, in every system operator, in every country, they give this information to the system operator, all the power plants, that what is the range of power they are interested in generating, and what is the value or what is the price at which they are interested in selling that power. Based on this, system operator finds the optimal solution, right? So for the hydro generators, they also submit the same information to the system operator, and these discharge related equations is taken care by the hydropower plants itself. So they, hydropower plants, does not give the discharge information to the system operator. They do their own study, they do their own analysis at their power plant level, and they find out how much power they can generate at a particular time interval, and they give this information to the system operator that okay, we can generate this much amount of power considering based on their own study, what they studied based on this discharge and the water availability. So the system operator just gets the information about the power generation variation, or the the range of power generation, and the price at which they want to sell this power. Right? Is it clear, Adam?
Yes, sir.
Good, good. Any more queries here? Okay, chalo, let us go ahead and just quickly see one small example which you can solve in the tutorial. Let me give you this example that let's assume there are two power plants in the system. There is one steam plant and one is hydropower plant. Both incremental cost and incremental water rate is given here. Their PS, the steam plant's maximum minimum limit is given, hydropower plant minimum and maximum limit is given, and you also have the load values here. Because here we are running for 24 hours. Let's assume from early morning at 12 a.m. till 9 a.m. the load is at 350 megawatt. From 9 a.m. to 6 p.m. it is 700 megawatt, and from 6 p.m. to night 12 a.m. the load is 350 megawatt again. So now when this type of problem is there, and you can assume that whenever power pH is 0, then pH is 0, then Q is also 0. Neglect the losses and assume that the thermal generators remains online for the 24 hour. So you need to find the PS value, that is the steam plant's power generation value, hydropower plant's power generation value for the 24-hour period, and assume that the total volume which is available for a day is 1250 million feet cube is there for total day. So just ensure that the dimensions are correct. Just check for the dimensions, because here it is feet cube I think, yeah, this will be fine. This is dimensions are correct. And ensure that this is the incremental cost and incremental water rate. So you have to convert this incremental water and steam rate to the cost function. So you have to integrate it. So you can just try it out again with the same tutorial. I'll add this also in the same tutorial, and this you can solve for the next tutorial session. And then if you have any queries, you can ask me in on Monday's class. Right, I'll upload this video and you can easily get the problem from here, and then you will get the understanding of it. Any queries on this question? You can take a minute and read it quickly, and if you have any queries for regarding the solution or regarding the solution of this problem, you can let me know. I think okay, Bahaldeen is having, okay, no problem, Bahaldeen. Okay, any queries on this question? Okay, if no queries, then let us go ahead and start our new topic, that is unit commitment. Shall we start that? I'll just give you a brief introduction. Anyways, from Monday onwards, we'll see the topic in detail, and probably 3 lectures I'll take to complete the unit commitment, and then we'll start the control aspect of power system. We are actually going into reverse time interval. I'll explain you that. Is there any query on this slide, or shall we go ahead? Anyone just confirm if we can go ahead on this? Okay, so the new topic we are starting is unit commitment. So anybody has idea on this, or just by the name you can see what do you understand just by the name unit commitment?
Whether the unit will be generating or not.
Yes, exactly. It's correct. So just by the name you can see that commitment is there. So commitment is a unit. A unit means basically in power plant, if you'll see, there will be so every generator is a unit, or unit matlab it's a simple sense, it's a generator, and now each generator are committed to generate a particular value at a particular time interval. So to simply say that you have to tell a generator when to switch on and when to switch off, and when to generate, when to not to generate, right? Now the question will be, why is it different from economic dispatch? Obviously on and off we can do also in the economic dispatch. Why are we studying this unit commitment separately? We can just add the on and off constraints and that can be satisfied in the economic dispatch. Why are we studying separately?
So to know the availability of the generation.
ठीक है, availability is fine. Availability, yes, we obviously based on and off constraints, we on and off variable which ensures that the generator will on or off. We can definitely know the availability also, but what else?
For forecasting.
Forecasting, no, not exactly. We actually assume all the data here. So we assume that we got the data from the forecasting.
Is there any limit on the?
Sorry, come again.
There's a minimum limit on generation.
Minimum limit of what?
Sir, on each generating unit, if we want to shut, if that's not optimal for us to operate that generating unit at all, still there is a minimum limit that uh, this amount of megawatt we have to dispatch.
ठीक है. Again, this is all about on and off. I agree on and off is there. Okay, so let me just again explain you this from a practical viewpoint. Think that you have a hydro, or sorry, not, take a coal-based power plant, right? So let's assume you have a coal-based power plant, and what happens is basically you burn the coal first, then you boil the water, and then water is converted to steam, and then steam is forced into the turbine, and then turbine rotates, and then turbine means the rotation of the turbine rotates the rotor of the generator and eventually generate the power, right? So this is the complete process of power generation. Now basically the idea here is that till the generator starts rotating, that is the extreme end or the last step. Before that, you have to first burn some coal to first, let's assume that the water is at the room temperature or at the normal temperature. So first you have to burn the coal, and then you have to boil the water at to some level of, obviously, to convert it into steam, and then you start generating power. So once it converts to steam, then obviously you immediately start generating power. Now the question is, during this process where you are boiling the water and converting to the steam, you are still burning some coal, but you are not generating any power, right? So basically, obviously, if a thermal power plant is there, or power generation is a business, think in terms of a business. All the power generators are owned by private companies or government companies. They are all running for profits, right? So all the businesses, if there is some raw material which is burning and you are using that raw material, who will pay for that raw material, right? So there is a question here that if that raw material is burning, that cost is also means that the power plants also require that cost to be recovered, and we have not discussed about that cost in the economic dispatch or in hydrothermal scheduling or in OPF. So in unit commitment, we will be actually considering these startup cost. So basically this type of cost of all the generators, in some sense it is required in nuclear generator also, it is required in diesel generator also, it requires in gas generator also, it requires in not except in hydro, you require in all the generators some startup cost is there in the power plants, right? I'm not sure if you have if you know this or not. Let's say if you have, let's say, two-wheelers. I assume that everybody have two-wheeler or four-wheeler vehicle. So let's say you must have observed or heard saying the car manufacturers or two-wheeler manufacturers that if, let's say, if you're going and you are stopping at a traffic light, and generally these days if you see in the traffic lights, you will see that there is going to be a countdown timer which will tell you that okay, after this time the signal will become green from red, right? So you must have observed, or you must have heard saying different manufacturers that if that time of that traffic light is less than 10 seconds or 15 seconds, then you do not need to switch off your car or switch off your two-wheeler you can keep it on and just remain 10-15 seconds at stop, and then as soon as it converts to green you can immediately start running your vehicle. But if the time is more than, let's say, 20 minutes or 20 seconds or 25 seconds or 30 seconds, then they say that okay, that now you can switch off your vehicle, and then you can wait till the time comes to 0, and then you can switch on and again start running your vehicle. So why they are saying this thing? Have anybody observed this thing, or have anybody heard this type of sentence before? And that was the
Yes,
main.
sir.
Yeah, good. So that was the main reason why even all the governments have installed a countdown timer at the traffic signals, because this is the way you can save your fuel economy, as well as you can save from the pollution also. Because once you start your vehicle, either it's a four-wheeler or a two-wheeler, immediately it requires a larger volume of oil than what if it is continuously at this on state. So there's a difference between that. So once you on, probably it might require, let's say, 10 ml of petrol, and once you are continuously running it, it might just require probably 1 ml for every 10 seconds or 20 seconds. So that is a trade-off, where they say that if your vehicle is remaining at on, then it is okay. If the traffic light is less than 15 seconds, you can keep it on, but if it is more than 50 seconds, you can switch off and wait for the signal to convert to green, and then you can start. So that is the trade-off. So therefore, in the diesel-based generators, even in the gas-based generators, there is some sort of small consumption of, because those generators are of big capacities, huge generators. So you can imagine, if we are talking about this small volume for a two-wheeler and four-wheeler, you can imagine the size of thermal generators or the diesel or gas-based generators, and you can imagine the amount of startup cost what they have to face. So these are the startup costs which are additional in the unit commitment, which we have not talked about or discussed about earlier. So this is the new thing which we are going to discuss, and even the optimization will ensure that okay, if the startup cost of a generator is higher and the operational cost is less, so it will obviously encourage a generator with a low startup cost and higher operational cost, or vice versa, depending on the situation of the system. So these factors has to be taken care. Also, once we are talking about the startup cost, there will also be a shutdown cost. So shutdown means basically a generator is synchronized with the grid, and as soon as we tell the generator to shut down, what you have to do, you just have to desynchronize the generator. And then once you desynchronize, basically if the generator is here and this is the grid is here, you just have to open this switch, right? You just have to open the switch, and then gradually this generators reduces the speed of the rotor and speed of the turbine, whatever way they are using. They can if it's a coal based power plant, you can stop burning the coal, but gradually because of the high pressure and high temperature, you cannot immediately stop burning the coal. So there's a process, there is a whole process that you gradually slowly start reducing the burning of the coal, and then gradually the temperature in the boiler starts reducing. So it's a whole lot of a process is there, which requires at the background once you tell a generator to switch off. So therefore those process also require some costs, and therefore these generators also ask that okay, once you tell me to shut down, you need to pay me an additional cost, which is a shutdown cost. This is being paid to all the generators, whatever they have asked for. So especially you can visualize this from the nuclear generators. Whenever you tell a nuclear generator to shut down, you have to do a lot of process, because obviously it's a radioactive material, it's a dangerous thing. So obviously there's a very lot of precaution and with a lot of caution, they do a process which will ensure to stop the nuclear reactor to start to from generating heat and from reacting. So it's a very careful process which people have to take care to ensure that you switch off the shut down the generator. So these factors are also there, which we are going to discuss in unit commitment. Also, there is minimum uptime and downtime constraints. These are the time, not minimum up and down time. So these are the time, basically the time interval. So what does this mean is basically, obviously, this startup cost or the process of starting up a thermal generator is not easy. Let's say if I talk again take you back to the four-wheeler or two-wheeler logic. So let's say if you switch on your four-wheeler and probably you just go to probably 100 meters and then again you switch off your vehicle and then again switch it on. So if you do that, then it becomes even more uneconomical or inefficient usage of that vehicle, right? So therefore, in the same logic, in the power plants, they also tell that, okay, once you switch on my power plant, keep it on till a particular time interval. You cannot tell me to switch off. Let's say generally from the thermal power plant point of view, or coal based power plant point of view, they say that, okay, if you switch on my generator, keep me switch on for, let's say, 3 hours. So if, let's say, if I tell a generator right now it is going to be 12 p.m. So if, let's say, I switch on that thermal or coal based generator now, I say that, okay, you can switch me on, but you cannot tell me to switch off till 3 p.m. Right? So these type of constraints make the operation of that power plant efficient. So these operations or these constraints are additionally considered in unit commitment for ensuring that units are committed in an efficient manner and in an economical manner. Right, so these time constraints are additionally there, which is called minimum uptime. So minimum uptime is basically awake. So once you wake me up, so keep me awake till this particular time interval, that is minimum uptime. Down is basically you are again going to sleep. So once I sleep, or once you shut down my generator, keep me shut down till this interval. So both constraints are there. So you have to ensure both up and down, and both has its own requirement. Every power plant has its own requirement on downtime and uptime. So the system operator has to ensure this minimum uptime, downtime for the efficient usage of those power plants as well as the economical usage of those power plants. Otherwise, power plants will face losses. Obviously, we as a system operator, he will not face anything. And also this switching on and off process, there are a lot of switches are there, lot of pumps are there, lot of various knobs are there in the power plant which you have to control. And if you often change all those settings, it creates wear and tear at various different levels, and it requires maintenance, or often maintenance will be required for those power plants if you tell them often to switch on and switch off. So to ensure everything, that the power plant, because every maintenance, I can tell you a quick example. Just if you call for maintenance for a power plant, generally for an hour, I can just give you an example. For an hour, for each hour, the power plant loses approximately 10 to 15 lakh rupees just if they go for maintenance. So it's not a small amount, it's a huge amount, and it's a huge loss for a power plant owner or a businessman who is running that power plant business. So therefore, they have to ensure those factors so that they can run efficiently and economically. So with this basic startup background of unit commitment, let us see that on Monday. I'll not go ahead because it's already 12 p.m. But I hope you got the basic idea why we are going for unit commitment, and and once you start the generator, then everything is same as economic dispatch or DCOPF or ACOPF. Everything comes after that. Once you switch on the generator, first you have to switch on the generator to include that in economic dispatch or DCOPF or ACOPF. Right, so this we are going to see in the next class, and we'll see the mathematics of it, how to solve it. There are a lot of different methods to solve this, so let us see all those in the next class on Monday. Okay, any queries?
Yes, sir.
Yes, please. Yes, please.
Am I audible?
Yeah, I can hear you. Baldi.
Yeah, I want to ask about startup.
Yes, please.
Yeah, it just means a startup is only for load light or what is called at night. We know that the load will be light. So at that time, I don't need to shut down the generators. So I think a startup is only for this period, or there are other cases for that.
No, startup can be at any time interval. Let's say a it does not have to take means startup cost does not is not related anywhere to the load. It is not the matter of the load. It is the matter of the generator. So if a generator is requested by the system operator to switch on, then that generator will have to do all the process which I was telling you about, the coal based power plant, that you have to burn the coal, you have to boil the water, and then at a particular temperature you start injecting the steam, and once you start injecting the steam, then only the rotor starts rotating and generates power. So this process actually can happen any time interval of the day. Means there is no specific time where I can tell you that okay, this time it will happen. It can happen anytime, and whenever it happens, it has some cost involved. That process involves some cost, and that cost has to be taken care as a startup cost while starting up, and then all the system operator has to pay that cost to these generators. But it can happen any time interval. It can happen at any time interval. Right?
Okay. We
are going to discuss this in detail. We are going to discuss this in detail in coming up classes.
Okay, sir.
Okay, you can also read in Wood and Wollenberg book. There are a lot of examples of unit commitment and basic understanding is given there. Most of the material what I'm taking is all from Wood and Wollenberg book, which is given in your curriculum as a references. That is the book which I am following the most for all the lectures. Okay, any more queries?
Yeah, I have question.
Yeah, please.
Yeah, it's related to generators. When we are at night and the load will be light, why we don't shut down the generators and start it again?
Yeah, no, yeah, you are right. Actually, we shut down the generators at night, because obviously at night the loads are very low, because obviously we switch off all the lights. Mostly all the commercial buildings are switch off, all the offices are closed, so most of the loads are off. So obviously at night time the load is very less, means compared to
but the cost of the starting again is more than I think it is because the generator needs maybe 3 hours or 4 hours to start again.
So what they do basically, let's say if the generator has to generate from 7 a.m. Let's assume from 7 a.m. he has to start generating. So what he will do that the system operator will inform the generator at 4 a.m. probably that okay, you have to start generating at 7 a.m. So start preparing the process. So everything is informed to the generator ahead in the advance, and they can take those actions. So there is no problem as such. And generally, if you'll see that obviously startup cost is high, but it is still not very high that it will go beyond the operational cost. So operational costs are less, but it is actually operational cost is multiplied over the time duration, but startup cost is paid only once, and that's why it's not very high. It's generally very less. but although it is less, even then we have to pay the generators. We cannot avoid those costs. And less, I don't mean it is just 1 or 2 rupees. It is still in thousands of rupees. So it's still a significant amount for an individual, but for a system operator it is not that huge amount, right?
Okay, sir.
Yeah,
Right, yeah.
yeah, good. Any more queries? Okay, then